Well, so we ended our last class discussion ionic emission. In that thermoionic emission, came across this Richard Dushman equation, which something like this. So I just want to illustrate a quick way to get physical information out of this thermoionic. Then we will move to our next very important topic, which is on wet dwarfs, application of Fermi statistics to description of dwarf stars. Anyway, let's quickly come to this Richard Dushman equation. So this equation looks like this, where is the work function, temperature is a constant. So since this has been already discussed in detail, so I'm describe everything this equation in much more details. Now we can rewrite this equation in this specific form. Basically, what we is taken t square to this side. So what one can do is measure current T and for different temperatures. So we can measure T for different temperatures. Then can plot this function J thermoionic T square. Then what we can get out of it, that data is something which is going to be very interesting. So okay, let us first see little mathematical manipulation, and then we will move to the physical aspect of this. So if we rearrange this equation, we found this, and here if we take log on both sides, we can find out here. So log of this quantity is equal to log of this whole thing, which is log of mn kind of expression, which is log of m plus log of n. But then this log of exponential of this function, exponential and log cancels with each other, and finally we get this equation. Now this equation is interesting actually. This equation is interesting in a sense that if we plot this left hand side, if we suppose experimentally measure thermoionic emission current of different temperatures and then obtain this J thermal over T square and take log of it and then plot that against temperature. So what we want to plot here is this equation is something like y equals mx plus c. You see, take this as y and 1 upon t as x. We take 1 upon t as x. Then what we can find out is that this equation becomes something like y equals m, this being the slope, x, because 1 upon t we are taking as x, and this is some sort of c, intercept of that line. So in that case, that's what we are going to see for any typical example of a metal. This is 1 by t. There's some problem here. It is a 1 by t plotted on the x-axis. So if this is so, then from this graph what we can find out is that the slope of this graph will be related to this phi and kb. So this is constant. So slope of this m is giving you m, right? So the slope of this graph will be actually related to the work function. You can just measure thermoionic current for different temperatures and plot the data in this specific manner, and from that data we can obtain the work function for that particular metal. So this is something really very useful useful application of this Richardson Boltzmann equation. Similarly, the intercept of this equation gives us the value of A. And now if you see the expression for A, this is made up of the fundamental constants only. 4 pi is a fixed number, m is the mass of the electron, and E is the charge of the electron, which is a fixed thing. And also we have AB as the Boltzmann constant, obviously, which is also a fixed number. So all these things are fixed. So from intercept, what do you expect? The intercept we expect for every metal to be same, isn't it? But then this can also differ a little for different metal based upon what is the effective mass. So instead of taking free electron mass, if there is a difference in you call the intercept, that can be attributed to the effective mass of the electron. So if intercept is higher than this standard value sorry, of say 120 ampere per centimeter square per Kelvin square, then that may be attributed to the effective mass. And I hope you have done what is the meaning of effective mass in your solid state physics course. So I'm not going into details. Sorry. Now let us come to next very interesting application of Fermi Dirac statistics, and that is to the white dwarf stars. So basically white dwarf stars are relatively very old stars. I hope you have gone through the stages of a star, its birth, and how hydrogen gas keeps on converting to helium, and a star keeps on radiating its energy out, and so on. So basically white dwarf stars are those stars which are relatively old, and they are almost in end phase of their lives, and they are having a specific characteristic that they have a small diameter, very faint in color. I mean, they don't emit much light. And why they don't emit much light? Because they have actually burnt out most of their hydrogen to helium, and that's why they have not been left with much light. There is the major factor, or the major physics of those stars lies in the gravity constituent matter of the star, which is mainly helium. And how does those um, helium atoms packed in a very dense star actually behave at such a high density? That's what is the fundamental concern of this topic. And we will see that how this Fermi Dirac statistics play a very crucial and important role in understanding of white dwarf stars. This Sirius B is one such white dwarf star. So probably, I think if you have done some course on astronomy, you would have gone through all those details. We are not going to discuss more details of stars here. We want to see the application of Fermi Dirac statistics to understand behavior of a star. That's the main concern here. So this say Sirius B is having a mass of something like 2 into 10 to 30 kg, which is roughly same as the mass of our sun. But interestingly, this star has a radius of only 5.57 into 10 to the 3 kilometers, which is roughly even less than the radius of our Earth. So just try to imagine that such a large mass, as large as comparable to our sun, has been packed in a very small radius of something like equivalent to our Earth's radius. So you can imagine how high would be the density. So that is why these white dwarf stars actually are the stars where the matter is packed at a very high density. So an idealized model for a white dwarf star can be expressed in terms of the following. A white dwarf star is usually a very large mass of helium, the order of say 10 to 30 kg. You can see this is typical value for one specific example. In general, we can find out, or it has been known, that the mass is of the order of 10 to 30 kg, and it is mainly the helium which is left out there because most of the hydrogen has burnt out, which is the star is in its last stage, so it's having mainly helium as its constituent matter. And the density for such case turns out to be of the order of 10 to 10 kg per meter cube. You can find it out by just dividing this mass with the volume corresponding to the sphere of radius of the order of this. Simply take pi 4 by 3 pi r cube. You will find out the density turns out to be of the order of this 10 to 10 kg per meter cube. And you can try to compare this density with the typical density of the matter around you. Say, try to take, say, density of iron, which you feel is reasonably very heavy material. So you would have felt weight of iron while you would have tried to lift some piece of iron rod. So try to compare those densities, and then you would find out that okay, this density is extremely high in comparison to the density of the matter which we are dealing here on Earth. Now, this is one thing that okay, the white dwarf star is having a mass. The order of this means it is a very large mass concentrated in a very small volume and having very high density, and of course is at a very high temperature, means those atoms of helium are actually at a very high temperature. They are having very large kinetic energy since this mass has been compressed in a very small volume. So for doing that, there must be a very high pressure inside, and then what other factor is there is gravity. So all those factors are resulting into a very high temperature, and typically that is of the order of 10 to the 7 Kelvin. This temperature of 10 to the 7 Kelvin corresponds to the mean thermal energy of each particle. That energy turns out to be of the order of 10 to the electron volt. Now you can take this temperature and then write down just simply kb into T, then find out the energy. This turns out to be of the order of 10 to the 3 electron volt. This energy is very much larger than the energy required for ionizing helium. So if atoms of helium in a white dwarf star are at a very high temperature, which is of the order of 10 to the 7 Kelvin, then their kinetic energy is such a high is in such a high value that the atoms of helium are all in their ionized state, because each atom of helium requires energy of 55 electrons to get ionized, and typical energy of the helium atoms is of the order of 10 to the 3, means 1000 electron volt. So definitely we can't expect helium to be in the form of neutral atomic form. It is like helium nuclei whose electrons have been ripped off because of their high kinetic energy, because of so many collisions they must be facing. Now, this means that whole helium in white dwarf is completely ionized. That's what we already discussed. Now, the constituents of such a star may be taken. Now, that's where our model actually begins. That's how we start writing down theory for any problem. Now we can write down that our star is mainly made up of electrons, each of, and of course n by 2 helium nuclei. So if we are taking n electrons in our system, then there has to be n by 2 nuclei, because helium atom contains 2 electrons, right? So mass of each electron is me, and mass of each nuclei is 4. Each helium nuclei is 4 times mass of the proton. I hope you understand what the helium nucleus contain. So in that case, total mass of our star can be written to be like this. Means this is n into me plus 4 mp to n2, isn't it? This is mass of each helium nucleus times number of helium nuclei, and this is number of electrons times mass of each electron, correct? If we follow the same, we can try to just express this in simple form. Just have common outside, and then uh, taken uh, LCM and then simplified it. So you can do, I think, simply. This 2 has cancelled. I mean, oh, then we don't even need to take LCM, right? So this will be n into me plus 2 mp. But now, since we know that the mass of electron is very, very less in comparison to the mass of the proton, right? Therefore, inside the bracket, this mass of electron, this term can be neglected. We can simply write down m is equal to this thing. Right? Now the number density of the electrons in the white dwarf can be estimated from the simple expression, right? Number of electrons per unit volume. You know, n is total number of electrons, correct? And then if we put expression for n, the number of electrons that will be equal to, say, m. Suppose this is the total mass, divide mass of the star, let us say, divided by 2 into mass of the proton. So from here we are trying to write down n actually. So n is equal to m over 2 into mp. That's what we have done here, divided by volume, which is nothing but mass over rho density. So if we rearrange these things, m will cancel. So what we will find out that number density comes out to be equal to rho over 2 mp, correct? Now electron density for this series B star comes out to be around 1.7 into 10 to the 36 electrons per meter cube, and this is extremely high density. If you compare this with the electron density in typical metals, earth, which we deal with, then the typical density for metals, electron density for the metals comes out to be of the order of 23 electrons per meter cube. So this is extremely high. It is 36. This is very high electron density. Now, if we calculate the Fermi energy corresponding to the electron, in this case, I hope you now are familiar with the formula for Fermi energy. Then that Fermi energy come out to be, from this expression, come out to be equal to almost like 0.33 mega electron volt. Now this Fermi energy is also very high. It's very high in comparison to the Fermi energy for electrons in typical metals. So the electrons in, say, white dwarf stars are entirely different system than those in the simple metals which we deal here on Earth. So this is an altogether a different aspect of Fermi Dirac statistics to a very high electron density system. Now, if we calculate Fermi temperature corresponding to this value of Fermi energy, which you know, this is nothing EF over kBT, you can work out the numbers, and then you will find out that this number comes out to be equal to 3.8 into 10 to the power 9 Kelvin. So I leave this to you to verify the numbers, because there are certain problems in this book regarding misprints. But yeah, this seems okay. This one comes out to be okay. Now this is Fermi temperature, fine. The rest mass of the electron is of the order of 0.5 mega electron. Now again, this you can find out in terms of energy. If you take mass of electron say of the order of 10 to the minus 31 kg, right? 9 point something into 10 to the 31 kg minus 31 kg, correct? And then use Einstein's expression E equals mc square. From there you should be able to find out the rust mass energy of electron, which turns out to be of the order of 0.5 mega electron volt. And you will be surprised to see that the Fermi energy of the electrons, of course, which is related to the kinetic energy, is, I mean, it's related to their number density mainly. But yes, when you go into details, you can relate this to what you call the Fermi velocity, and hence to their kinetic energy to some extent. Exactly. So these are comparable, right? And this is what makes the things more interesting. So basically, the dynamics of electrons in a typical white dwarf star has to be treated relativistically because the rest mass energy of electron is of the order or at least comparable to the kinetic energy of the electrons, right? So we must actually apply relativistic mechanics to that, relativistic equations for this system of electrons, and that's what makes this system altogether different from the situation of electrons in a metal. And statistically speaking, the electron gas is in a state of complete degeneracy. Now again, hope you remember our previous lecture. What's the condition for being complete, for, for a system to be completely degenerate? The condition was that ratio of temperature is to Fermi temperature should be very less in comparison to 1, and this ratio for these particular numbers turns out to be of the order of 10 to the minus 3, because typically the temperature of white dwarf star is of the order of 10 to the 7, and the temperature is of the order of 10 to the power 9 or 10 to the 10. This number turns out to be of the order of this. You can find out the rough numbers, so these will work out. And main thing to be noticed here is that it is not close to 1, it's very less than 1, and that is what makes our system to be identical to a completely degenerate system, which is something like, okay, Fermi Dirac system at absolute 0 Kelvin. We can take this we can take the formulae for the completely degenerate for Fermi Dirac systems here, and then try to describe the white dwarf stars. The core of Sirius is, of course, at 2 into 10 to the 7, so you can work out those numbers. I leave it to you. So this highly degenerate electron gas actually behaves essentially as an electron gas at absolute 0, which I already discussed. Now, the pressure exerted by an ideal fermion gas at absolute 0 Sirius for the Sirius B is of the order of 1.8 into 10 to the power 2 Newton per meter square. Now you will ask me from where this pressure came. So I hope you remember our previous lecture where we had discussed completely degenerate Fermi Dirac system. There we had obtained an expression for pressure. So in that expression, if you put these numbers, you should be able to get this value of pressure on gas in Series B. Again, I leave this as an exercise to you, so you can try this. So this pressure actually turns out to be approximately the order of 10 to the 17 atmosphere. Now you can imagine here on surface of Earth we are living in 1 atmosphere pressure. So what is the pressure on the core of Sirius B is extremely large pressure, right? Then there is a question that, okay, if there is such a large pressure core, what holds the core together? Why doesn't it blast? Isn't it? because this is such a high pressure. In case of metals, we had given an argument. Okay, then we had calculated the pressure in case of metal as well, and that was also very high in comparison to the uh, this one, atmospheric pressure. But then the reason for stability of metal was presence of atomic nuclei there, which were somehow holding them together. But here on this Sirius B star, the main reason for this to be, this nuclear and electronic interaction can't be that strong to hold that star together at such a high pressure. That's not sufficient. And the main whose cause for binding of this star is actually the gravitational attraction, which is mainly coming because of the helium nuclei. It's not Coulomb interaction, electrostatic interaction, or even dynamic interaction, but mainly the gravitational attraction, which is playing a very crucial role there. Now, don't try to say that, okay, the nuclei are very small, electrons are very small, how do we expect gravitational pull to be so strong? Now, try to see that the mass there is very high. Even if you take the example of Sun and Earth system or our solar system, the mass is coming because of the helium nuclei, Sun, hydrogen or helium nuclei on Sun. So this is like, okay, what is the overall total mass? So that is playing an important role there. And in Sirius B or in any white dwarf star, the mass is very high. And that is why the gravity dominates, or gravity is really dominant enough to deal with this high pressure. That's what is the moral of this story. Now, okay, let us try to make our life somewhat simple and do some assumptions. The assumptions are that, okay, the dynamics of our system is governed by electrons mainly. Means in white dwarf star, it's the electrons which are the main parameters, or which are main constituents which actually decides the properties of our system. That's the first thing which we are assuming. Why so? Because we want to just get away with the application of Fermi Dirac statistics to understand system of white dwarf stars, and for that we just need to stick to the electronic system. Don't need to bother about what nuclei are doing. We just will say they are kind of acting as a source for gravitational pull, not more than that. And second thing is that the electron gas is uniformly distributed in the star. That's our second assumption. This is so electron density is uniform. It's not non-uniform. Actually, it may not be the case. So any deviation of experimental observations from the theoretical results which we are going to obtain here may be attributed to the incompleteness of these assumptions, right? So if you have to get more accurate results, you have to get away with these assumptions and then try to incorporate more and more different changes there. So anyhow, let's move ahead. Now to discuss the ground state properties of an ideal Fermi gas of n relativistic electrons, know that we have to actually talk of relativistic electrons. Now, since their rest mass of and mass energy and kinetic energies are comparable to each other, so we can write down the Fermi energy is of course known by this expression, and here from here we can write down n, the number of electrons is given by this. This is just rearrangement of this equation, so you can work it out yourself. Now, if we use an expression for Fermi momentum, this is just like P, this is just okay. Energy is equal to P square by 2m. Right? Since we are dealing with the free electron, mainly they are kinetic energy as the dominant energy. That's why we are only taking kinetic energy. This is P square by 2m. From where we can find out P, and then we actually want to find out the momentum corresponding to the Fermi energy. So that's called Fermi momentum, you can say. this turns out to be equal to 2m and EF under the root. Now, if we do so, we can get the same expression for this n in terms of EF. So you just put the value here, you can find out this will be nothing but EF cube. And from here we can estimate the value of PF, which is equal to this. So from here we just rearranged the terms here and then obtained PF is equal to this number, right? This expression. Now let us keep this in our notes. We will be using this expression. Now since we have to now consider our electrons relativistically, so we have to use this expression for energy. Energy is equal to square C square PL. I hope you remember why L is here, to not confuse ourselves between pressure and momentum. So PL means momentum. If you write P only, that would refer to pressure. Fine. So this is our relativistic expression for energy. Therefore, the ground state of the system is given by what? So this is given by E naught is equal just an integral E naught to V over H cube. This is nothing but that expression integral over E into dE, where energy is going from 0 to EF. I hope you remember that completely degenerate systems expression. So in this case, we have written this integral in terms of actually momentum as a variable. So this is energy part E, this is our dE part. dE part means energy in the volume momentum space in the sphere, say 4 pi PL square in dPL, means sphere in momentum space radius PL and between PL and PL plus dP. So I hope you can make it out yourself. So this gives us the total energy for this electron gas inside a white dwarf star. We have just applied Dirac statistics and relativity. Now, if we simplify this expression, then this turns out to be, so what we have done here is actually written this 4 pi outside uh, over h cube, this, so where and here what we have done, so you have to be little cautious here. I mean, you may see that okay, if this 4 pi has come here, where have this 2 gone, right? So you try to work out, but what we have done here is that we have taken mc square common. This is square root of this thing. From, I mean, this is something like this. We are taking mc square common out from here. So what we will be left with this is 1 here, right? Because you take m square c raised to power 4 common out of this bracket, this is square root, then it will come out in the only mc square. It's a very simple thing. This is 1 plus PL over ME into C whole square. So this is P squared C squared, that is fine. But then this is divided by C raised to the power 4, right? So this C raised to the power 4 and being divided with C, I mean C squared divided with C raised to the power 4 will be leaving, or you will be left with 1 over C square kind of thing. So this is the same thing. So PL over, this is simple, okay, under root. So PL square dPL, right? This is same. I'm still confused why they have missed this factor of 2 here. Let me check quickly. What? No, I couldn't find. So sorry, try to work, try to uh, find it out why they have missed it. This probably is a typo, but still, if you find out some more reasonable thing, you can just let me know. But this won't change the physics much. This physics remains almost unaffected. Apart from a factor of 2, everything else conceptually will be the same. It has to be there, yeah. It seems it has to be there, right? Because there is no expansion applied here as such. So fine. Let us see. So let us now make a substitution for this PL over ME into C to be X. So we're just trying to do a change of variable so that can writing from here P square dP will be now you can try to do this. From here you can say okay, P is this, and what will be dP? dP is equal to ME into C to this side into dx. And then when I write P square will be nothing but M square C square X square, right? And then M1 MC coming because of dP. That's why we have cube here. So this will become something like this. This is again simple thing, you can try it. Now limits of integration also would go from 0. So PL goes to 0. From here you can see as PL goes to 0, X goes to 0. And as PL goes to PF, what would X go to? X would go to PF over ME into C. You just have to substitute PF instead of PL, right? Fermi Momentum. So this we are writing with XF. So this therefore this integral now here they have replaced this 8 with 4 with 8. So this had to be actually 8. This is something confusing thing in this book. There are some small confusing things here, but don't just if you use this book carefully, it's fairly useful for course contents. So this is 8 pi v m e raised to the power 4 c raised to power 5. Now that's what we have done. We have substituted this, so you can simplify these things. I leave it to you. So now E naught is equal to 8 pi. Now what we have done is, okay, we have been writing that okay, this integral will lead us to some function of xf, because limit, when you will solve this integral, then you will find out some function of x. When you will substitute the limits, then you will find out that is going to be nothing but a function of xf, the variable x corresponding to Fermi momentum. And if we see this fx, f turns out to be equal to this. This is the integral which we have to find out. This integral turns out to be equal to this, and there are two conditions here. When xf is very less than 1, and when xf is very greater than 1. So basically what you have to try is, you have to try here binomial expansion. This integral would be pretty simple. You have to try binomial expansion and then solve this integral. Or one situation when x goes up to xf, of course, but xf is very small in comparison to 1. And second case, try for xf being very large in comparison to 1. So you will be finding that, I leave it as an exercise to you guys. So this will be okay. This expression will be coming for this, and then this will be the expression that will be coming for this. This comes out well. I have tried it, at least this one I have tried myself. I leave it to you. You try it. So it comes well. Now, okay. Now this, what does physically this mean? xf being very less than 1. This one. What does this physically mean? This actually corresponds to non-relativistic case. And xf being very larger than 1, it actually refers to relativistic case. Why so? Let us look at this expression. Now if you see here, if xf is very less than 1, what does it mean? This number is very less than 1, correct? If this number is very less than 1, c is velocity of light here. If this number is less than 1, what does it mean is that pf over me has to be less than 1, correct? It has to be very less than c, correct? And this means that this is related to the velocity of the particle, correct? I mean, this is momentum divided by mass. It is related to velocity of the electron. So this, if this means that velocity of the electron is very less in comparison to velocity of light, and that is why this turns out to be very less in comparison to 1, and that is why this refers to the non-relativistic case. Now second case will be whenever this happens to be very large in comparison to 1, then that refers to the relativistic case. Now here you may fall into a fusion. I mean, how can velocity of electron be greater than the velocity of light, isn't it? After all, we know that nothing can travel faster than the velocity of light. Basically, this uh, has something to do with the group velocity and phase velocity. So this is representing phase velocity, which can be greater than velocity of light. So that's okay. Nothing very here. Now, I mean, whenever we will be talking of a non-relativistic case, we will be taking xf to be very less than 1 condition. And we are going to talk about relativistic case, we will be putting this condition. So whenever we are talking for non-relativistic case, we shall be using this expression for this, and whenever we will be talking about relativistic case, we will be taking this expression. Now let's, okay, fine. This further, okay, we have made some further substitution here. I mean, this, so from where this has come, we have just put the value of this Fermi momentum. Hope you remember we have done it. It's, I think, here in the previous slide itself even. This is our Fermi momentum, right? We have put this expression of Fermi momentum here, and that's what we have got after this. Fine. Now, okay, we know the volume is equal to 4 by 3 pi r cube. We know the mass, which we had written well in the beginning of this presentation. This is how we can write this. So if I try to find out n over v, the number density actually, number of electrons per unit. So this turns out from here, let us say this is n, this is v. So this will be 3m by 8 pi m r cube. So you just have to rearrange things here. Take 2mp here, and then rearrange things. You can easily. Now, well, if we know this, and we have been using this xf, you know what is xf? Is this this one rather? Here we can now substitute the value of n over v. So basically, not even putting here v, what we have been doing here is, this is h over me into c. Yes, h over me into c, this part. And why he still has kept n here? Just a moment. This thing is so he has put this n over b is perfectly fine. xf is equal to yeah, there is again a blunder which he has done here. This should not be n, this should be actually m. So please correct it in the book itself. This is a we also fix it up in book. This has to be M. Fine. Now fine. So this has to be M. 9 pi M over 8 MP. Of course. This is 3M for this thing. So and 3 multiplied by n over v, that's what we have put here. That's what you are going to get finally. This, and in the next step he has fixed it up. So this expression for xf can be written in short form to be like this, where we are saying, okay, let us say this number, this is m now, okay, this number is m. Now he has fixed in the next step itself 9 pi m divided by 8 this. So if we take this to be m bar actually, then this is m bar raised to power 1 by 3. Let us say this number is nothing but 1 over r bar, so that r bar is equal to r. So you can compare from here, r bar is equal to r into whole of this expression, and this is something, you know, you're familiar with this. This is nothing but the Compton wavelength for the electron, isn't it? So um, this is actually the expression for radius, some r bar actually, in terms of Compton's wavelength of the electron. Anyhow, um, now let us move next to find out. So now we have described the xf here, and from that has been described in terms of this. Now one more thing here is to notice is that this m bar is directly proportional to mass of the star. So this is some sort of effective mass. You don't say technically effective mass, but it is related to mass, you can say. This is mass. This is mass actually, sort of apart from some constant factors. And this is related to radius. You can see this r bar is related to radius because all these are fixed numbers, constants, right? This is related to the radius. So this is actually simplified expression just to get rid of all these lengthy expressions. That's all. So if we now want to write down the pressure for such gas of fermions, then that can be written to be this expression. I hope you've done this. So we know what is energy. Now energy was equal to this. Hope you are able to see it, recall it from the previous slide. No, I don't want to go to this slide, but yes, energy was equal to that integral actually. So this was the value of that integral, and now we know that what is this. So that's how we can write down the energy. And now if we find out pressure, this is energy only. We are now taking derivative of energy with respect to volume. This is constant, this part is constant as such, so this is sitting here. This is pressure, so it should be P naught, not E naught. Please be cautious. It's P naught is equal to this thing minus sign as such. Now here is where we have to take care of the derivative. So this has to be, or this can be seen as to be made up of two functions. Actually, one thing is f xf. Oh, volume is sitting here as well. So apart from this, apart from volume, everything else has been taken off. So this is like first function, second function, right? So derivative will be one like this is first function, derivative of second function with respect to volume. So this is second function means derivative of volume with respect to give you 1. That's your first function only. And for second function part, volume is kept taken out, and then derivative of this with respect to will be that by chain rule you can say del f xf over with respect to, say, let us take it with respect to xf and then take derivative of xf with respect to volume itself. So this will be del f over del v itself. And if so, now we know that xf is equal to pf over me into c. We have seen it here itself. Now if we from this expression actually try to find out del xf over del v, then you can take the derivative. This is a standard simple derivative. This remains as a constant outside the derivative, and this also remains as a constant. Even n can be taken outside, and then you can take, okay, let's take this as a constant first, and we have to take the derivative of this raised to the power n. So this is n into this whole raised to the power n minus 1. So this is 1 by 3 minus 1 is 2 by 3 into derivative of this with respect to. So you can find out. Fine. So you can simplify this further, and you can find it out that this comes out to be 3v minus 1 over 3v. This one, see here, right? So this number itself is what? 3n over 8v 8 pi v square. So from here what we are doing is, okay, let me take v out here, so that's why it is minus 1 by 3v, like this, and then we are left with h over me into c. This is as such. Now this is 3n over by v is to a minus 2 by 3, and this is also 3n by v, since one of the v has been taken here. This is the same number raised to the power minus 2 by 3. This is the same number raised to the power 1. The minus has already been taken, so the powers can be added. This is minus 2 by 3 plus 1. This turns out to be equal to 1 by 3. Just simplified. And if we actually have to find out this v into del xf over del v, so we just have to use del xf over del v and multiplying it with v. So this will give us minus 1 by 3. This v should cancel then. This is nothing but xf. You can see this is nothing but the xf. So v into del xf over del v is minus 1 by 3 xf. Clear? So this term and this term effectively gives us minus 1 by 3 xf. Now let us proceed to obtain this value del f over del xf, and for that, now, yeah, for this part we have to proceed in two different ways. One is for non-relativistic case, which is this one. So now we have to take the derivative of this with respect to xf, and this is this one. So again, this can be divided into two functions. This is, say, first function. Let us take this as a second function. So what will be the derivative? This will be first function. Let me say this one is the first function. For timing, let us say this is the first function. This will be first function as such, derivative of second function. So this is 1 by 3 into derivative of this. This will be 3xf square. So 3 cancels with 3. This will be nothing but xf square, plus this is the second function as such, derivative of first function. You can see, and then derivative of this goes 0. This is 3 by 10, and what will this give you? 2xf, right? And 2 cancels 10 and results into 5. So this will be 3 by 5 xf. So that's what we have found. We don't want higher order terms. So what we will finally find out from here is, you can take xf square common, and then what is left here is 1 plus, now you can see from here, right, 1, and then what else is there for xf square? Yeah, here you can see this is xf raised to the power 4, right? 3 and 1, xf raised to the power 4. When you take taken xf square outside, then you will be left with 3 by 15 xf square inside the bracket. So you have 3 by 15 xf square plus 3 by 10 xf square. So what will that be? Oh, 3 by 15. No, that's not 3 by 15, sorry. Yeah, 3 by 15, that is nothing but, yeah, it is just 1 by 5. So this is 3 by 10 plus 1 by 5. So does it come out to be equal to half? should 3 by 10, let's do it on notebook, plus plus 1 by 5. So 10 and 10 is the LCM, and then you can find out 3 plus 2. This is 5 by 10. Yeah, this is half. So effectively, this turns out to be half. Okay, now let us discuss the next case, which is for relativistic situation where SF is very large. In same way, we can proceed. So you can take this expression now, and then have to proceed same way for this. So then you can find out that this turns out to be equal to this. Again, you have to try first function, second function, and I leave it to you as a homework. I'm sure you all can do this. If there is a problem, you can try to you can ask me the problem. So now since we have all the things which are required to write down pressure, because okay, that's what we require for pressure. So this is actually describing the pressure. Now we have this, we have obtained this, so we just have to substitute the values. Again, you have to be a little careful with your notes, and then finally you can find out that this pressure can be written by this expression. So all these substitution, this is just a substitution job, I can leave it to you. But yes, this is the interesting expression, the pressure. Now now we shall be using this pressure. Okay, what we have done here actually is we have done some simplification here. What is that simplification? Is that we have substituted the value of fx. So we have fx, that long expression here. I hope you know. Yeah, this is your fx for two different cases. So the task is going to be little lengthy when you do it on your notebook and when you have to obtain the steps. But I recommend you do it so as to understand that it's not a black box, but it indeed comes out to be correctly. So I leave it to you. So here we have to substitute that values of fx, corresponding values actually, in this equation and then things will cancel, and certain terms will cancel, and finally what you will obtain is that the pressure, this white dwarf star, comes out to be equal to this simple expression for xf being very less than 1, that is the relativistic case. The second case is when it is relativistic case. So this turns out to be equal to this. Now this is something very useful which we are going to use to describe our white dwarf star. I hope you have not lost into this, you have not been lost into this mathematics. Our main objective is to understand those white dwarf stars. So what we have done till now is we have tried to write down the expression for pressure because of electron gas inside the white dwarf star, and this is the pressure which has been obtained by applying Fermi Dirac statistics as well as the relativistic expression for the energy. So from where is Fermi Dirac statistics coming? We have been using the formulae from our previous lecture on, say, completely degenerate Fermi Dirac systems, right? So the Fermi Dirac statistics is already put in there, and then relativistic aspect of the energy of the electrons has also been put up. So that's what is giving us this important expression for the pressure due to electron gas inside the white dwarf star. So okay, I have written here, you have to put these values here and then obtain this. So that's okay. Now will come the physics part of all this mathematics. the complex mathematics which we have done. It's not very complex, it's just simple those basic plus two formulae of derivatives. But yes, the expressions are lengthier, and that's where you have to be careful in obtaining them. Now, this is something very interesting, the mass radius relation. And this mass radius relation uh, is going to describe the interesting physics of our white dwarf stars. So the pressure exerted by the electron gas in the white dwarf is actually counterbalanced by the gravitational attraction between the helium atoms. That's what we were talking in the beginning. Now this pressure, okay, the gravitational potential, if let us now try to write down the expression for the gravitational potential. This is very simple, right? So this is minus alpha gm square over r. Here g is the gravitational constant, m is the total mass of the white dwarf star, r is the radius of the star. That gives you the gravitational potential. Alpha is a constant which is close to 1. We won't be talking much about alpha, right? So these again, so these parameters we already described. Now the change in energy of the star due to work done against the pressure is given by how much change in energy if the star does some pressure. This will be equal to P naught r 4 pi r square dr. Uh, this is pressure. You know, energy is nothing but force into distance traveled. So pressure into area. This is area of a sphere of radius r. So this is force. This is force, right? Is the distance. If suppose the star changes its radius by say dr, how much energy would be changed can be obtained by this expression. Now here we have expressed this pressure as a function of radius, of course. So depending upon the radius. Where is that dependence coming? It is coming in xf. Try to go back to the expression, detailed expression for xf. We'll be coming to this. White star, white dwarf stars, the configuration, for the configuration to be in equilibrium, suppose the star is at an equilibrium at a specific point time where it is not expanding nor getting compressed because of gravity. So this is actually a counterbalance between the natural pressure and the gravitational force. The pressure is trying to expand the star outwards, and the gravity is trying to pull it inwards. That's what we are trying to say, that in equilibrium, this two has to be same. Du gravitational has to be equal to the, the pressure energy, right? From here, we can simplify this or rearrange the things to obtain the value for P naught R. This is just rearranging the things. So this 4 pi r square goes here, dr cancels on the both sides. So this is just the expression for the pressure as a function of radius. Now I hope you remember what was m bar and r bar. If we actually use those m bar and r bar, then we can write down the expression for so what we have actually done here is that we have actually written m in terms of m bar and r in terms of r bar in this expression. So m square means this thing 8 p over 9 pi whole square. So this thing actually. So this is here what we have done is we have written m in terms of m bar. So similarly r in terms of, we have replaced r. So take this term to this left hand side and then these things. So now actually what we do is we're trying to write down the pressure in terms of m bar and r bar along with all these fundamental constants. Why so? Because these numbers are these variables m bar and r bar, something interesting for us, and we are going to see this shortly. Now, this expression exhibits a remarkable combination of three tools of theoretical physics. This expression, three very interesting tools of physics sitting in it. Now, those three tools, try to guess. One is quantum mechanics, which we have applied, and we have been applying Fermi Dirac statistics. I hope you know that it was quantum mechanics which was coming from the condition that the de Broglie wavelength of the particles is comparable to the interparticle separation. That is what all has gone into the recipe of obtaining the Fermi Dirac statistics, the fermions, and that's what is crucial here. Means, and why is it required in white dwarf stars? Because the electrons are so closely packed inside the system that they have to be treated quantum mechanically. Second ingredient is relativity. I mean, the particles are moving at very high speeds, so we have also to bring into picture the relativity. And third thing is gravitation. So this formula is a very interesting soup kind of thing of three interesting ingredients: quantum physics, relativity, and gravitation. And that's why it will lead to a very interesting physics which is going to come. Now, well, this is the expression for pressure P naught, which we have obtained in terms of xf. Now you would say, okay, there is another expression for P here. How are the two related? Right. So now let us try to compare these two for two different cases. One is for non-relativistic and another one is for relativistic. So now if we stick to non-relativistic case, you will find out, okay, non-relativistic case xf is very less than 1. What we have to use, we can put xf, which we have defined earlier. Xf is nothing but m raised to the power 1 by 3 divided by m bar raised to power 3 divided by. I hope we have done it earlier. That's how you can express xf in terms of m bar r bar. Fine. If so, then let us put xf here and then equate that with this thing. Fine. If we do so, then what we will be finding, okay, you will be getting some expression like this, but you would say, oh, this is really a very black box kind of expression. How it has come in detail. Basically, if you try to say, I mean, this is in this equation there is a k dash sitting, so you have to put actually this thing to this left hand side, and this is sitting already in the right hand side. And in left hand side, you will be finding that you have 4 by 5 k m bar raised to the power 5 by 3. So from where that 5 by 3 is coming? 5 by 3 is coming from this. This is xf, actually raised to the power 5. And then in xf itself, it is actually nothing but m bar raised to the power 1 by 3, isn't it? So if you see left hand side, so okay, in left hand side we have 4 by 5 factor. So from where that factor of 4 by 5 k coming? So k is given by this expression, and which is coming from this actually, this one. So you can see it is 8 pi m e raised to the power 4 c raised to power 2. So this is 8. I mean 2 raised to power 3 would be 8. Now you would say, oh, it is pi cube, but then It's not pi cube, actually it's pi, because pi cube will get cancelled with pi square due to this pi, and you would say, okay, it is me raised to the power 4. So this is me, and this is me cube, so it's me 4. Then you would say, okay, this is c square here it is c5, so it is c square here, c cube, this is c raised to power 5. You would say, oh, it is 15 here, right? It's cube, then 15, and then here is 12, right? Why so? So don't worry, we have 4 by 5 here sitting, so it will accordingly transform to this thing. You can now, try to simplify. Just simply put these values here, you will come up to that length equation. Now I'm not doing the details, I leave again it to you, but yes, this is how you can obtain. Fine. Now k dash, again on right hand side you could see, this is what is k dash, is just same thing, alpha g over 8 pi, isn't it? Alpha g over, you would say, oh, 4 pi, it is 8 pi, right? And that also probably is because of rearrangement of things. And try to see, okay, this is as such here, this is as such, this is 2 pi me c over h whole raised to power 4, this is also as such. Now here is a factor of 8, here is a factor of 4, and this factor of 4, this factor of 5, all these together when put, you will find out, okay, you finally can actually arrive at this equation. Let's not make it more lengthy, so I leave it to you, but you can do it yourself in your notebook. Now this expression can also be rewritten as this form. What we have done here is, so you have here m bar raised to the power 5 by 3, this m bar raised to the power 2. So if I take it this to the left hand side, it will be m bar raised to the power 5 by 3 minus 2, which will be nothing, m bar raised to the power 3. Now it is r bar raised to the power 5, right? If I take this there, this will be just r raised to the r bar, this will be just r bar. Okay, now 5 by 3 minus 2 will be minus 1 by 3, right? So we have actually taken this to this side, just simple rearrangement. Again, I'm not going into detail, but yes, rearranging the things, you can arrive at this. So this thing is crucial here actually. Left hand side, this is m bar raised to the power 3 r bar. This is equal to 4 by 5 k over k dash. So you can take k dash to this side and all other things to this side. Then you will be able to this expression. Here you put the values of k dash and k and k dash, take their ratio, and you can obtain some number here, m naught raised to the power 2 by 3. So where m naught is nothing but k over k dash to the power 3 by 2. Again, this is just rearrangement. I have been trying to put term in terms of 2 by 3 here. It's nothing very complex. This is put here k dash, k by k dash raised to 3 by 2 whole raised to power 2 by 3. 2 by 3, this will turn out k by k dash only. So nothing to be confused about. This is form which is going to be useful to us. Now you can find out what it's going to be. So you can put k dash, k, and then the values. Now from here we can obtain a very interesting relation between radius, the white dwarf star, and mass of the white dwarf star. What will that be? So this m naught is, you can see here, this m naught is made up of all these fundamental constants here. This is fixed, this is fixed, this is fixed, this is fixed. C, speed of light, Planck's constant. So this is some fundamental constant in itself, and this defines a sort of mass. What will that be? We are going to see it shortly. So from here we can find out, okay, from this expression we can find out that R bar will be equal to 4 by 5 times m naught square over m bar whole raised to power by 3. That's why we try to incorporate uh, the 2 by 3 here to make this expression look like this. Now that's fine. So keep this expression with you for non-relativistic case. Same way we can do the same thing for a relativistic case. And for that we have to follow with this equation. Now I leave this as a homework to you, where you have to use SF, the same expression as we have already defined, and then P naught, you have to use this equation, then put XF here, from here, rearrange the things, and then finally the equation which you will arrive at will be looking like this. Again, this is a sort of homework to you. You try it yourself. Now, if you see from here, you will find out that R bar is equal to m bar raised to the power 1 3. Again, here is a rearrangement actually sitting. So I also leave this to you to do this rearrangement yourself. But the main message of the story is that R bar, the relation between the radius, because R bar is related to the radius itself. I hope you remember that previous expression which we discussed in previous slide. R bar, the radius, is related to m bar, mass of the star, by this expression in case it is a relativistic situation. And for white dwarf star, of course, we are going to deal with the relativistic case because that is a relativistic case. And we can also try to put the corresponding non-relativistic results. So this is how the two results compare. Fine, you can try to see. The main physics comes now here. And what is the moral of the story here is that for a non-relativistic case, the radius of white dwarf star is inversely proportional to its mass, because this is m bar raised to the power 3. So m bar is related to mass itself. So we can say radius is inversely proportional to 1 by 3. So whenever a star is heading to its end stage, I mean, it's not still reached to the level of being a white dwarf, then what is then this can be termed as a non-relativistic case. Then what happens is that its radius is inversely proportional to its mass. Larger is the mass, smaller will be the radius, or what we can say is large mass will be uh, packed in small radius. Large mass would correspond to the smaller radius. This is something really strange, something which we should notice carefully. Smaller the radius, greater will be the mass. Means a star would be going to, if it is shrinking down, what is going to happen is it will be taking, I mean, okay, it depends upon what is the star and how much mass it contains. Accordingly, it will be having smaller radius. That's the simple thing which we should notice here. Uh, or larger is the mass of the star, smaller will be the radius. This means that star will become relatively denser with the passage of the time. That's how you can again try to say this. That over the time, star will try to reduce its radius and accordingly go on approaching towards the relativistic limit, and this will be going from this description to this description, and that's what will make it more interesting. Or on the other hand side, if we try to see for relativistic case, then we can see here that here there is no problem, but here is a problem, that we have a number sitting here m naught. Now in this equation you should see that if m naught is less than m bar, then what happens? Then m bar is greater. And this term, this term will be greater than 1, right? This term is greater than 1. This term as a whole will also be greater than 1. And then this thing will be less than 1. And you're taking square root of it. So that would lead to something physically invalid, right? So this mass limit in itself is trying to hint towards a situation when, I mean, uh, under which if the mass of the star is, if the mass of the star is greater than this limit, then it would go to a very small radius, you would say. You can say, okay, if mass is approaching 1, when mass is 1, when m bar is equal to m naught, radius is 0. You can say that, okay, heavier is the star, smaller will be the radius. One situation will come that when the mass becomes comparable with this mass m naught, the radius has to be close to 0. And that is something which we can relate to the gravitational collapse of the star, when the the pressure is not sufficient to actually hold the star at some finite radius, and it will collapse down. Now this m naught, let's try to talk about this. We have seen what is the expression for m naught in our previous slide itself. Now here we can see this number is made up of all these fundamental constants, which corresponds to a very small size white dwarf star. Whenever m is comparable to m naught, then we would say that radius is very small. That's what he's trying to say here. Now we can therefore conclude that no white dwarf star can have a mass greater than m naught, isn't it? You can say that white dwarf stars, if this m is greater than m naught, that would lead to something very strange. R bar is not defined. This thing is not defined, right? So that's physically inconsistent. So means in case that happens, if that mass goes beyond this, then that can lead to a star collapsing into a single point, and that may lead to something very different, like a supernova, or leading, or this star going to a black hole, something like this. So that is where this limit, or this limiting value of m naught is something very important, and this is related to the Chandrasekhara limit, which we will be seeing. So physically, what does it mean? Physically, I already told you the same thing. And physically, this means that mass, if if the mass of the star is more than this limit m naught, then the pressure of the electrons inside the star is not sufficient enough so that it could hold the gravitational pull, and hence it won't be able to support the electron gans against the tendency of the gravitational collapse. So if the mass of the star is greater than m naught, it would lead to the gravitational collapse of the star. And okay, in this expression, if we take alpha to be approximately close to 1, then we will find out that this number turns out to be close to 10 to the power 30 kg. And that is why most of the white dwarf stars have their mass to 10 to the power 30 kg. If it is greater than that, what will happen? Gravitational collapse. So Chandrasekhar worked out somewhat more details on obtaining this m naught in more details, and what he found is that actually this m naught, if it actually is equal to 1.44 times this one. This is actually nothing but the solar mass of our sun, which is oh, it's not given here. Okay, now you refer to the book. So this theta refers to the mass of the sun, which is 2 into 10 to the 30 kg. So these features are now depicted in this figure. This is what you should notice from here. This is solar radius of our sun. This is r over r theta, and this is m over m theta, mass of the star over solar mass. So what you would find out is, okay, whenever this m is very less in comparison to m theta, sorry, then it has some finite radius, white dwarf star, and then that radius keeps on decreasing as you increase the mass. You can see that from this expression. This radius will decrease as m will increase. You can try to write a Fortran program and obtain the expression or obtain the plot for R bar. So that would lead you to plot looking similar to this one. And not exactly this one, because Chandrasekhar did some modification, which is not sitting here in this formula, in this m naught. Fine. Anyhow, then when you reach a value close to 1.44 of the solar mass, then that is this thing is actually denoting the gravitational collapse. The radius suddenly decreases down. So this is called gravitational collapse. So what is Chandrasekhara limit? It is the value of the limiting mass for a white dwarf star, beyond which, if any star possesses a mass larger than this Chandrasekhara limit, then that star would exhibit a gravitational collapse and can lead to a supernova or formation of black hole, something like this. That's something important. With this, we complete our this unit on Fermi Dirac statistics. My next few lectures will be devoted to the Bose-Einstein statistics. We have already done it, most of it. So I feel only few lecture would be sufficient. I will be completing them soon. I mean, I would need, I think, 2 to 3 lectures for getting this thing done. But those lectures are going to be important because I will cover many important topics in those lectures. So please don't miss those lectures. So thank you. Stay safe. Good luck for your exams.